And welcome to the Desk of Ladyada.
Hey everybody, and welcome to a Monday evening Desk of Ladyada. We're back with part 2 of a F-1000 part series, many part series on this MEMS microphone stuff I'm playing with. So what we covered yesterday is we talked about how the Circuit Playground board has a MEMS microphone on. It's an analog MEMS mic, and the reason I went with a MEMS, not electret mic, is even though it's a little more expensive, it's surface mount friendly and it's flat, no through-hole soldering. You can put it through a reflow oven, so that makes for easy manufacturing. But the trade-off is I wanted to get rid of all the analog amplification section that goes with it, because the signal that comes out of these MEMS mics is very low voltage, a couple millivolts. And so on this circuit, I amplify it like 100, maybe 200 times, something like that, to get it to an analog signal that can be read by, an AVR or a Cortex N0. But then I was thinking, maybe with the processing power of the SAMD for the next version of Circuit Playground, I can maybe update it from an analog to a MEMS mic. And so last night we showed off the PCM, the I2S type of microphone. So a quick review. You've got the analog mic. That's what I've got right now. And over time, the signal we get is an actual analog signal. And this is, maybe 3 volts, 0 volts. And I actually sample that analog signal, and when it's loud, the peaks are higher, and when it's quiet, it kind of settles around, about 1.5 volts. The center voltage of my range. And so, it's very easy to measure this signal, because I just use analog read on the pin, and it gives me, a value from between 0 and 1024. Middle range is about 512, something like that. Super easy to use. So that's what traditional Circuit Playground used with an analog MEMS mic. And then last night I tried playing around with an I2S mic. An I2S is digital, so when you read the data from it, it actually comes out not as an analog, but as a digital signal. And the way that works is you actually have a clock that goes up and down 32 times. And then you actually get from bit 0, this is bit 31, comes first, to bit 0, you actually get a digital signal. So, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, something like that. And this is a binary representation of the data. So when it's very loud, it's going to be 1, 1, 1, 1, 1, and then when it's very quiet, 0, 0, 0, and then literally, 1, it's binary, like 0x1 is pretty quiet, a little bit louder is 0x2, a little bit louder is 0x3, all the way up to 0x7FFFFFFFF. So, a wide range, but it's digitally coded, and you read it by measuring the signal from the clock rate. And this is, it's a little bit more complicated than analog reading, because you have to get that pulse going at about a megahertz. The microphone actually wants you to clock it at a certain speed or it'll go to sleep. And then you have to read that binary data, and then you just, put it into an integer, and you read the value. It's not too bad. I mean, it's basically a lot like SPI, right? You're clocking data in or clocking data out. That's how I2S microphones and amplifiers work. And so this is, basically got this working. You can use on the SAMD processor DMA, which is a way of basically telling the chip to say, go and do this procedure of clocking in 32 bits at a time. Go do that, 1,000 times, come back to me when you're done, and you have like a big chunk of data that you can do stuff with. So you don't have to read every signal, every single signal you don't have to read. You can actually tell the processor to help you out. And this is really great. These work well, but there's a couple things that I don't like about I2S mics. One is they're always bottom port for reasons I don't completely understand. So the signal, you have to mount the microphone on the bottom of the PCB and drill a hole through it. whereas the PDM and analog mics are top port available, so that you can mount them on the top of the PCB. So that's like kind of one trade-off. And the other one is there's a lot more PDM mics. It's much more common to get a PDM type mic than an I2S mic or even analog mic. I mean, like, it seems like every single company makes a PDM MEMS microphone. I think that a lot of cell phones, that's what they use. They usually have more processing capability. And so they can use like the lower level, kind of a more bare metal interface called PDM, which is pulse density modulation. And this is similar to PWM, except instead of having, an 8-bit word that you change the modulation, it's single bit. And it's actually really hard to draw PDM. And so I actually have some nice images that I found online from like Wikipedia and stuff. So I can show those off. And it'll be a little easier to understand what they look like. This is a MEMS transducer. So this is a kind of a nice image showing PDM. Or this is a good image. So you have the signal. Oh, do you want me to? Hold on. There you go. Yeah. So you have your 1-bit signal going up and down, and the density of these tells you where in this sine wave, for example, you're at. So when you have perfectly balanced pulses, it's kind of like a 0. And if you have like more zero, if you have the same number of ones and zeros, it flattens out. And when you have more zeros and ones, it dips. I think also Wikipedia had a good. Let me find where this came from. Wikipedia. Pulse width pulse density modulation. So I had a good image too. So also like this, you can see the more ones you get, the higher the value. So it's kind of like, it's a little bit like PWM in that, it's the more ones you get. It's a kind of it's a very analog-y digital signal. It's not like an encoded binary signal where like you chunk it off and it's like an actual number. You're actually looking at how many ones you have with respect to how many zeros you have to determine where you are in the wave. Now, the thing that this image doesn't show is you actually have like hundreds of ones and zeros. Like the number of bits you have is really, really high because, for example, if you're, let's say you have a 32-bit, you're getting 32 bits of signal, and you're getting you're getting a 3 megahertz signal. So, and your actual output is maybe like 20 kilohertz. So you have like a 3 megabit per second, and then you divide that by your 20 kilohertz. You'll have like 150 bits per sample. So you actually have a lot of these ones and zeros to kind of average out for each audio sample.
So Telecrate in the chat says, alternative to reading a PWM signal directly is a low-pass filter, resistor plus cap, and using an analog in pin you most likely already have on your microcontroller.
Yeah, you'd think so. And actually, I tried that. And the answer is, in theory, as long as you have a low-pass filter, you can get rid of this incredibly high frequency, that 3 megahertz wave. The problem is that the kind of filters that you would build on your breadboard, like let's say you took a very basic RC filter, your RC filter, right, it's, sorry. Your filter here, and you have your output here. This is actually, because I was just trying, I was like, and I can show it on the breadboard. Having even a simple RC filter, a low-pass filter like this, it's not sharp enough. So this is only a 1-pole filter. So right, you've got your frequency, and you've got your, if you know your thing, it's what is it, 3 dB. can't remember what's the pole, how many dB drop you get per octave, but this is your frequency, so this is your RC filter. You need this to be like that. You need 11 poles, something 10 or 11 poles, more than just one. So you could do this with a bunch of op amps, and before you know it, like your breadboard is just covered in op amps because you have to have such an insane filter.
Okay, Alex says Delta Sigma DACs encode data in a similar way.
Yes, in fact, it's inside of it is a Sigma Delta converter. So that's why I'm like, when I was researching this, I was looking at PDM, because this is like all totally new to me. I've never worked with PDM before, and it's like, oh yeah, basically this is just the output of your Sigma Delta. But you need to have so you could, in theory, do this in analog, but your signal's going to suck. Like, it's not going to be pretty at all. And I can show in the breadboard, because I tried it. I was like, like, what if I just make a basic, filter with, 10 or 20 kilohertz as the roll off, and it was like barely good enough. You could barely see that, even if it was blowing on the mic, you could barely see a signal. You need something way better than what you're going to get with a basic RC filter. So this is why these are almost always going to go into your DSP or your codec. You're going to have specialty circuitry to do that filtering. If your signal output is real, like 20 decades below 3 megahertz, maybe you can get some signal out. But I couldn't get any 10 kilohertz-ish signal out of a 3 megahertz input. It didn't show up. Actually, I'm not even doing 3 megahertz. I'm doing it 1 megahertz. So, I lose even more than that. So this is the PDM. So I can actually show some of the examples of what this stuff looks like on the oscilloscope cam. So let's go and trigger. Okay, so this is my I2S clock. And let's start with doing the I2S so we can compare the I2S. Because it's kind of interesting. It's like, basically the I2S mic has all this decimation and filtering on it already. And then, hold on, give me a second. I have to get the blue signal connected to this output. Okay, so this is that the right signal? Hold on. All my lines here are blue. Yeah, so this is the digital signal. It's actually kind of hard to tell, but if you look at the video from yesterday, yeah, there you go. It's a little easier to trigger that way. You can see that it's actually like it's binary data, right? And you're getting maybe like 14 bits here of actual usable data, and then this is the left-right clock stuff that we talked about yesterday. So you can do when you normally get this data, you have left, and then your right microphone would be here. I only take one side of the stereo signal. I'm only doing mono. So this is what this is PCM I2S data. So this is what that looks like. And what's interesting is, of course, the clock is the same because it's still a digital clock. So I actually wired them up so they both share the same clock line. And then if I move this to, hold on, here, you can see this is the PDM data. So the PDM data, there is no structure. Like, you saw in that other signal, there was like a structure to it. You could see like the beginning of the data and the end of the data, and there were, is it packetized in a sense? Like, there's 32 bits. You could tell what the start was, the end was, because there was you get 4 bits high and then 4 bits low. Where the PDM data, it's just like a total mess. I mean, it's just raw bits. There's like no way to really view this easily. So let's use our Arduino to grab that data, and I'm going to take my analog mic out of here so I can hook it up, and we'll look at what it looks like on the Arduino. Oh, so I can show this. Hold on. Flippy. So this is my SAMD, and this is that bottom port I2S mic, so you can see there's a hole in the bottom because the microphone's on the other side. So this is what the microphone looks like. This is like a breakout that I didn't end up using. So it's the microphone, and there's no hole in it. The hole's in the bottom. So that hole in the center, that's a ground pad, but it's also the hole where the audio gets sensed from. So this is annoying because it's like if you're trying to put the microphone on the top of a circuit board, you can't. You have to basically do a double-sided design to get the audio to come out that way. This is the PDM microphone, and it has a port on the top. So that's that. Okay, so back to the computer. So the I2S code that we were hacking on yesterday is pretty simple. You read a signal from I2S. Every other word is going to be all Fs because it's the opposite side of the data, right? Because again, we are only taking the mono channel, but the I2S core will give us a stereo. It's kind of you set it up for stereo no matter what. And so we toss out that, and then if the sample is 0, it's because we over pulled data or something, so return. According to the data sheet, only the top 14 bits are even valid, so we toss out, the top 18 bits are valid, toss out the bottom 14 bits, and then you can map it. And then if you look at the video, we actually got fairly good signal output. The biggest issue I had was I was getting desynced with the DMA. If I was going to use this in the final circuit playground, I'd probably have a custom, because I control the entire chip, people aren't going to show up at the circuit playground and try to do more I2S stuff. I'd probably pare down the I2S to be custom and just for circuit playground audio reading. So I probably wouldn't get out of sync with the DMA. I would actually call the interrupt directly and use that to process the data instead of having multiple layers of buffering. And then I could buffer that to the analog output. Anyways, so this worked great. Check out the video from yesterday for more of that. Now on to the PDM. And PDM is a little different. I even started doing some decimation stuff, but let's start with a new fresh sketch. And I can delete a lot of the stuff, and then we'll rewrite it as necessary. So let's start with, we won't decimate anything. Yeah, this is fine. So what we're going to do in this loop is we're going to get basically 64 samples from, and it'll show you why you need to grab so many samples at the same time. You're going to grab 64 words, 64 words, 32-bit words from the DMA. I just have a little LED that just toggles to let me know, so I can look on the oscilloscope to see, when am I processing, reading data. I read it, that many samples. I just iterate through from 0 to number of samples I want to grab. And then this is a uint32 that contains those samples. Now remember, the samples are single bits. It's kind of weird. And then I have digital low, and then what I'll do is I'll just, I'll print them out in hex. We'll see how that looks. So we'll just call this PDM demo. And what's neat is actually you're just using the I2S core of the SAMD chip. So the SAMD is meant to grab that PCM data, but you can use it to grab PDM data. It's just not going to do any of the conversion for you. It's going to give you raw bits, as you'll see. Okay, so when you look at the serial monitor, there's just data. And if I stop this, it's just, there's no real rhyme or reason to it. It's just bits. It wasn't like when we looked at the PCM data where when it was quiet, the number was low, and then when it got loud, the number got higher. Because this is a pulse density, you actually have to look at the individual bits. So what we're going to do next is I'm going to grab my my code here. It's kind of ugly, but it works fine. Instead of printing the raw sample in hex, what I'll do is I'll iterate over every bit, and I'll make a raw sample equals Oh wait, there's two I's here. That's not good. Change to J. Oops. I think it doesn't actually matter, but it's a good idea. Okay, so for each one of the samples, I'll go from the most significant bit to the least significant bit, and I will print an X if that bit is set, and I'll print a blank, a space, if that bit is not set, and then I will print a return. And this is this one and that one. Okay, good, it's balanced. And let's look at the output now. Enumerate? Okay. So now this is like the literal bits. I'm just like, this is like the matrix, but for PDM, right? You're looking at the actual bits as they're printed out. An X is a 1 and a blank is a 0. So you don't see anything. And actually, that makes a little bit of sense because it's not that loud here. I mean, even though I'm kind of yelling, you're not going to be able to really see that. Also, this is delayed. The output is delayed because like I'm printing and like the DMA buffer's filling and like I'm grabbing the data later. So you'll notice it's a little bit out of sync. But then when I take the microphone and I blow on it, you'll notice the pattern changes. And then I can try to maybe scroll up to see that section. Okay, so this is when I was blowing on it. See how it went from being like this kind of nice, almost every other X in space is balanced, to now the X's are way more dense. Where X is pulse density modulation, there's more X's here because the amplitude of the waveform that it's reading is higher. And then later on, it's like, you can tell it pegs at the bottom because it's all zeros. And then back up to, you can see it's like, okay, so it's the density increases and decreases. And whatever, actually I read a paper that was interesting. It reminded me of dithering. You know, like when you look at comic books. We were looking at the those cards. Do you have that card still?
No,
but cards. But when they do the printing,
yeah, you can probably just take something from that's printed there. I don't know. There'll probably be dots on it.
Yeah, it's probably dot. You want to look at it under the microscope? Right now, under the microscope, we've got the PDM microphone. But let's see what happens if I just take this.
Yeah.
Yeah. Okay. So see how this is made with dots, right? Like when you print color, you don't have infinite inks. Like this is, you can see the blue, the green, the red dots are all mixed up. So especially here, you can see the mix of blue, green, and red to make that kind of purplish color. Hold on. This is kind of a pain to... Okay, so here's a good spot. I'll zoom in. Other way. Zooming. Focus. Okay, I think that's good, right?
Mm-hmm.
So you can see the blue, red, and green dots. And this is actually the same thing as pulse density modulation, right? It's the same idea. You see when you want a light green color, you have that background and you have little green dots kind of spaced evenly. And then on the curve of that, a C or whatever character it is, there's higher density where it wants to be like a blacker, a darker blue. There's medium density in the middle. And then to make that highlight, there's a lighter density of dots. Same exact idea, right? And then how does this filter? Well, your eyes filter it. When you look at it from far away, your eyes filter the color for you because you can't see that high resolution. So this is kind of like your eyeballs are doing the filtering for you. I mean, if you look really closely, you're like, oh yeah, I can see the dots, but that noise kind of goes away into the background. So it's the same idea, right? But this is with audio data. So the next step you have to do is you have to decimate it and then filter it. And again, if we have a moment, maybe I'll put an RC filter on. You can see how it's like, it totally doesn't really help. But the next step we can do is decimating. So you got those ones and zeros. What we can do is, and this is not an intelligent way of doing the decimation, what we can do is just take 4 sets of 32 bits at a time. And then we literally count how many ones and how many zeros. And then you balance that out and we come up with a number. And that will give us, because right now we can't graph what we have because it's just ones and zeros. It's just like bits. We have to turn that into like number. And actually that's what my original code did. So I'll just go back to my original code. So what I do here is, so we've got those raw samples, and then I have the decimated samples. And we pick how much decimation we want. Basically, how many bits are we going to count the number ones and zeros? I'm going to say 32 bits because that's four bytes, but actually what I meant was 4 words. And then we will do that same thing where we read in all the samples we need. And then you have some debug data here, but I will go through in samples, and this is where I had that, print X or 0, but instead what I'll do is I'll sum the number of ones and zeros. So if the sample, if that bit of the sample is 1, I add 1 to the sum, and if that bit is 0, so I go through each one of those bytes, and if it's 0, I subtract. If it's 1, I add. And so if you have a perfect pulse density modulation, you'll get, for example, if there's actually perfect quiet, it'll be perfect number of zeros and ones. They'll completely balance out because it's like a neutral gray of color. You'll get 0. And if it's a really low value, you'll get like a negative number. And if it's a really high value, you'll get a 1. Now there's smarter ways to do decimation. This is very slow, but it's very easy to explain on a webcast. So I'll delete this just so I don't need that debug data. I don't really need this print line either. Yeah, so I grab my sample, I set the sum to 0, and then I decimate over multiple bytes at a time. Yeah, what's up?
So someone wants to know, do you have to pull off the bits faster than the DMA is being filled up?
You do, but remember, your DMA is going to go get a ton of data, and there's very fast ways to decimate. I mean, this is like shifting and adding, and there's lookup tables you can use. This is really fast. This is at the fast part of the filtering. It's the later stage, which I haven't written yet, that's a little tougher, where you actually have to do low pass. But the good news is for the stuff that I'm doing, I'm not going to be streaming stereo microphone data. Like what I actually saw is, there's you can get 8 microphone arrays, because that's what's going on in the Google Home. They have 8 PDM mics, and they're streaming the data and doing math and calculation. For that, yes, you will want an FPGA or a DSP core that will be able to do the filtering very fast. For me, I actually have enough memory. I'm not getting CD quality audio. I just want verbal quality audio. So I'm probably only going to need 8 kilohertz or maybe 16 kilohertz sampling to get, basic music or speech. When somebody's speaking, it'll get the sound pressure level, maybe some basic FFT. So what I can do is actually read a whole chunk of data, and then, I can get a couple seconds worth of data or a second's worth of data, and then do all my filtering on that, and then I'll get the result I want. I don't have to stream constantly. I can do it in chunks.
Do any of the ways of decimating preserve the concept of bit significance, or does that not matter?
It doesn't matter, because if you think about it with pulse density, each bit stands completely on its own. There is no significance to where the bit is. That's why it's a little easier in a sense to decode than PCM. With PCM, you have to start reading at the exact right time to get that most significant bit down to the least significant bit. With PCM, I can literally listen whenever I want, and that density of dots, I can, you can read it immediately. So it's another thing. If I want to sample data, even though I can use the DMA, I can DMA as little or as much as I want, and then just filter that chunk of data. As long as I get enough samples, and I think I did the math right, I need 150 samples, bits per audio sample at 16 kilohertz, I'm good to go. That's actually not that much data. But if you think about how much data you need, and the decimation is very fast. Getting the data from the DMA and then decimating it will take way less time than it is to read that data in, I think. And especially if I do lookup tables, and I can process it in chunks. And again, the DMA doesn't take any time whatsoever. That happens in the background. If I can decimate it now, like, I've taken all of these bits and I've compressed them down quite a bit. I mean, you probably should have a DSP for this, and I think 48 megahertz can do it. I can calculate how many cycles I need. It was like 48 megahertz divided by 16 kilosounds. So I have like 3,000 instructions per sample. I think that's going to be enough. Because this stuff, the decimation is order n, very fast. You just go through it. And it can actually be faster than order n, because instead of going through each bit, you can use a lookup table. So you have a lookup table and you can look up 8 bits at a time. So you can do the decimation of 1 byte worth of data in like 8 instructions. Just cool. But for now, I'm just doing this stupid way. Just going through each bit, shift it, compare it, some high, some low. And then I'll store it, but for now, I can also print it out. So let's see what happens. And that's kind of the end of this experiment, because I have to learn about digital filtering now. Digital filtering is like the one thing I kind of didn't really study that well in school. Analog filtering, I built a lot of analog filters. Digital filters, I vaguely remember doing it in MATLAB. But I also seem to, that part of my brain got recycled for other uses or something. So I have to relearn that. Okay, so now we look at the data. So this is, again, decimated. You know what? It keeps crashing for some reason. And this is adding the number of zeros and ones. So this is for every, 128 bits. This is the balance of zeros and ones. In this sample, I got, there would be 6 more zeros than ones. This sample is actually trying to be exactly the same number. So you can tell this is very low amplitude data. Reset it. The DMA gets stuck. And let's try the plotter. Okay, so again, the plotter auto adjusts to amplitude, so it looks like really, really noisy, but actually it's because it's just bouncing between like 0 and -8. And when I speak really close to it, you can actually kind of sort of see audio. Like again, I'm not doing any low pass filtering at this time other than that decimation, but you can sort of see a audio waveform appearing. I have to be really close because I not have any filters. I kind of have to fight the noise, but it is there. So that's the most basic output. So it's basically just to prove like the data I'm getting is correct data, which is kind of good. You want to make sure that your pinouts are correct. So that tells me if my pinouts are correct. So the next step, again, I have to take that decimated data, and I think there's smarter ways of doing it where you do a running decimation. So right now I'm taking chunks and like I'm decimating this chunk and decimating this chunk. But what I probably want to do is have like a moving average. So I take multiple, I decimate, but I decimate every bit's worth. So I get, instead of taking 128 bits and turning that into one sample, I maybe would, oversample that and have like 8 samples. So I have more to work with when I take it to the low pass filter next. But there's still a lot of digital noise, as you can tell, that I have to fight through. Like, the analog sensor would be able to hear the audio from this distance to the dev board, but the PDM mic, if the signal's there, I have to fight a little bit harder to get it. I think it's there and I can get it, but I have to filter a whole bunch more out to extract that data. So we'll see. If I can do this, that'll be really handy. Question is whether I have enough processing power and whether I can, basically design a digital filter. Like, kind of all the example code I found was like only for chips that have a built-in DSP, and it was like distributed as a blob. So it's like, okay, I got to go back and read about how to do a filter. But apparently, all I need is like something like a 10-pole low-pass filter, and I'll be able to get that audio signal out.
In the chat room, some people said the ham radio community is interested in a lot of digital filtering because of the SDR designs that are out. And then Alex in the chat said that he knows digital filtering and he's maybe looking for work. So I told him to email me.
Yeah, sure. You want to design me a filter? I mean, the thing is I personally am slightly ashamed and curious about digital filters because I remember I took the class in it, and I remember making all the lollipop diagrams, and I cannot remember a single thing beyond that. I just completely erased that from my brain. So this was like 10 years ago. So the next thing is I could show what this looks like with a simple RC filter, but like you won't be able to see almost anything. But for the one person who's interested.
Yeah, sure.
Okay. Okay, so.
What are we doing?
What? So let me go. It'll be. I'll
You put that under the overhead?
Yeah, I'm gonna put this on the overhead, and then I have to design a basic RC filter, and for this, I will do. Yeah. Okay, so let's use a tool like. Let me see. Here you go. Okay, so I can do a basic computation. Let's say I'm going to grab a 0.1 microfarad and I want the cutoff to be, well, let's be generous. Let's say 10 kilohertz. So I need about 160 ohms. So let me grab this stuff. Give me a moment. In my bin. I have to read the little numbers. 104. 104 is 0.1. And then resistors. I think I have a couple 100-ish ohm resistors. That's a little bit much to ask it to output, but we'll see. Maybe it can. I have a 220 ohm, which is probably what I'll just have to deal with. Okay, so can you go to the overheady?
Tell Creighton chat. It says 150 worked for.
What?
It said 150 worked. 150.
For what?
I don't know.
Okay.
I'm trying to keep up with 8 things.
Yeah, I know.
I'm like, I don't know, 150? Sure.
Sure.
Are you trying to figure out a number?
Okay. Yeah, numbers are good. Okay, so this is, let's get this data out.
Maybe for the calculations? I don't know.
I don't know either. Okay, so this is that data. Oh, sorry.
150 ohms.
Yeah, something like that. Okay, so let's do this. And then do that. And measure there. Okay. Let me trigger on channel. Sorry, setting up my scope here. You can kind of see something. Okay, so let's go to, the scope cam. So you can see down here, that's my digital PDM signal. And this is my RC filter at the top. So I actually want to, again, I'm going to go pretty low here. And then if I blow into this, you get something. But apparently it's like right now it should be able to, like I'm getting lost in the little noise there, I think. I might also be filtering out some useful signal. Let me trigger on channel 1. I mean, you can kind of get something. But apparently, like if you really want to get something good, you have to do a digital signaling. Hold on. Oh no, this. Let's see, 1 AC couple. We'll move this down. Can you see anything?
Yeah.
Yeah, I mean, you do get, if I'm really close, you can get some signal level out. You can see it's a little noisy, but. Oh man, I gotta replace this knob. Yeah, so you can sort of see if I'm really close, you can see some audio signal coming out. So you can filter it.
You're communicating with an oscilloscope.
Yes, but it's tough. Like from this distance, you see there's still, you can see a little bit. you can see a little bit of the signal, but I still have a lot of digital noise on top of it. So this is where I would probably get, you would get an op amp and actually have like an active filter. But then you're back to where we were before, where
we don't want hardware. We want to do this in software.
we want to do it in software. But you can see, I mean, like the signal's there. It's there. It's just even though we cut out a lot of that.
You need some math.
A lot of that that 3 megahertz signal, it's still there in a sense. But you can tell it's like PDM. If you really wanted to, you could connect it to an analog input. This is what I got earlier. But I think I can do better with a digital signal, and I think I have enough clock cycles to do it in. So I basically want to, have this is a single pole filter. So if I have a digital filter, but I have like I don't know, like 6 or 7 poles, I'd be better off. It's like a really sharp cutoff. Get rid of all that high frequency, because it's just like you're getting such a huge amount of high frequency noise. Okay, that's how it works. Dithering. PDM mics. So the next step for me is learning how to do digital filters. And what I actually am probably going to do, because it's a little bit, because again, the DMA crashes sometimes, and I don't really want to go into the library and figure out why, because I don't really care. Like, I'm probably not going to use that library anyways. What I'm probably going to do is just grab a ton of data, and I could what I'll do on my Arduino, I'll probably just like get like a buffer of like 16 kilobytes of samples, because I can just buffer that in memory, because it's got 32K RAM. I'll set aside half the buffer, fill it with raw bit data from PDM, write it to the SD card, take out the SD card, and then use like Python or something to actually do the filtering. Because again, if it's digital filtering, you can do it with any programming language. I don't have to do it real time. So instead of like writing code, uploading, I want to get the filter as good as possible, and then I can always squeeze it into the amount of time I have on the Cortex M0. But like for actually developing a filter, doing it with Arduino is a little bit. If I knew how to do it, I would just do it. But since I don't know how to do it, I'm going to learn in Python, where I can like do like PyMath and graph shit and like have a good time. And I'll probably play a 1 kilohertz sine tone, so I'll know exactly what the output signal should look like, and then I can optimize that code and then port it back into C. That's what I'm going to do next. And then K-Town gave me a really good suggestion for a book. Can we just go to the computer real quick? So I was like, hey, K-Town, do you know anything about digital filtering? Because I don't. And he's just like, oh yeah, I do. Check out this really good book. It's The Scientist Engineer's Guide to Digital Signal Processing. And it's like online too, but you can also buy it. It's dspguide.com. I started reading a couple chapters, and it's like kind of coming back to me. So if you're interested in it, and what I like about it is it's uses like real words. So the issue that I found when reading online about digital signal processing, it's all everything that's written online is kind of written for people who've already done DSP. So they're like, okay, so get your CIC IR boxcar filter, and I'm like, I don't know what these things are, but that's like the introduction. So what's nice about this fellow is when he writes, he's like, it's a moving average. You know what a moving average is, and he also shows like what the signal will look like before and after, and he has like pseudo random. So he's like, here's what it looks like beforehand, and here's what it looks like with an 11-point moving average, and a 51 moving average. So he kind of talks about like this is what it really looks like, and he has some basic, like literally basic pseudo code that you can use if you're trying to understand what that means for you actually implementing it. But like this stuff, it's not, there's not that much math, but you just want to get it right. So yeah, he's like, oh, here's the summation, but then he's like, here's what it actually looks like, and this is how you actually write the code. So exciting. Yeah. Okay, that's what I got for tonight.
That's it?
Yeah, I think that's plenty.
That was a lot.
If anyone has any really good links for PDM filters and suggestions for if you've seen, it's like, oh, I know a project that does this because I kind of looked around and I couldn't find anything, send it to us. And we'll
you can email pt@adafruit.com.
Post in the chat or something.
That'll help us out quite a bit if you want to, participate in this. wonderful project. You
Yeah.
can see the oscilloscope right here. Make some noise.
Test. Hello, hello, hello.
She's making some noise.
Test.
Yeah.
Hello, hello, hello. That's not so bad, you know.
Yeah.
You could actually, you know what you could do? You could actually read this with the analog digital converter, and you save yourself like one pin. But I don't know. I'm gonna try to do it using the digital inputs. Because I think the thing is, the analog microphone I have right now is actually quite good, and it uses the exact same circuitry inside. So if I can get it working, like as long as I can implement what they implemented, the sensor itself I know can do it.
Yeah.
I just have to get that data out. Filters. I think actually digital filter. Maybe I did digital filters once. I remember I made an EKG, and I designed a filter that would do the band pass for the EKG, because EKG is very fixed band. So I think I remember doing that. Word.
Okay.
So that's my news.
All right.
You want to go inside the chip?
Yeah. So we're going to shut down some of the stuff here. Desk of Ladyada is brought to you by you, the customer out there. Please purchase something from Adafruit.com, and that helps pay the bills here. Tonight's background video, we start to turn off all the cameras here, is iPhone 7 is decapping the right?
This looks like a reballing.
Yeah, and this came from a tweet from Bunny. So we subscribe to the channel. It's like a G Tour or something like that. It's pretty rad.
This person's amazing.
Yeah, so you can see.
Look at this crazy insanity.
Yeah.
I'm always like, I'm soldering 0.4 millimeter QFNs. Like, ooh, look at me. Okay, yeah. I'm not reballing like. I don't even know what the pitch is on this.
Yeah, it's crazy.
0.3 millimeter BGA.
Yeah, last night we had a video of an egg machine.
Yeah, this is pretty cool too.
Anyways, so that's it. That's Ladyada.
It's a lot of flux.
Yeah.
Maybe it's the UV curable stuff.
All right, so that's it.
All right.
Pick up something at Adafruit.com.
Good night, folks.
Thanks, y'all. Say bye.
Bye.